So let's look at a math example of this now. So we have this statement we want to prove. The sum of the first n positive integers is n times n plus 1 over 2. First, let's just think about what this is saying. This is saying that as long as I add up a bunch of numbers in succession, the positive integers, so let's say it's the first 5 positive integers, so an n is 5, then 1 plus 2 plus 3 plus 4 plus 5 should be the same as 5 times 5 plus 1 over 2. Well, this is 15, and if I add these numbers up, I also get 15. So that's what this is saying, that I can use this formula to calculate the sum of a set of numbers that is the first n positive integers using this formula instead of having to go through and add every number up. So we want to prove this using induction. So when we write our proof, the first thing we're going to do is say what we're trying to prove. So to prove, and when I write this to prove statement, the reason we're rewriting it here, even though it's in the question, is also to write it in a more friendly format. So the sum of the first n positive integers, that's a lot of words. It doesn't help us with equations. We want to convert words into some numbers and equations to use. So instead of writing it as the sum of the first n positive integers, I'm going to write that out as, what does that actually mean? It means if I go 1 plus 2 plus 3 all the way to plus n, it should equal n times n plus 1 over 2. Now we're going to go into our proof step. So first thing we'll show is the inductive hypothesis. And that's where I make my supposition. I'm going to say, suppose that this worked for some number. For example, we know it works for 5, so we're supposing it works for 5. Right? So suppose, or you could say assume, that for n equals k, 1 plus 2 plus 3, and so on, up to k, would be k times k plus 1 over 2. Right, so we're just selecting some number. We don't know what that number is. It could be 5, it could be 10, it could be 2. We're just saying that for some number, let's just say this works. Well, if it works for some number, then we're going to show that it should work for the number right after it. So for the inductive step, we want to show that it also works for n equals k plus 1. 1 plus 2 plus 3 plus k plus 1, the next number, should equal k plus 1 times k plus 2 divided by 2. And so I'm just substituting k plus 1 in for n in that formula. So we're supposing it works for something. Now we want to show it works for the number right after it. So we got to do some math on this. So if I'm looking at my left side of this equation, this is like when we prove trig identities. We're working on one side of the equation and we want to make it look like the other side. So my right side is set. I know that's what it needs to equal. So I'm going to work on my left side to make it look like the right side. I have this ... on the left side, which means I don't know how many numbers exist in there. So we want to find a way to get around it. Well, what I can do is I can notice that I have this piece is the same as this piece. And I said that this 1 plus 2 plus 3 all the way to k equals k times k plus 1 over 2. So I can substitute that in. I can say that all of this equals k times k plus 1 divided by 2. Every time we do induction, we make this inductive hypothesis, where we suppose that something is true. The reason we're supposing it is because we want to use it in our proof. We don't like making unnecessary assumptions, because if we make assumptions that aren't necessary, that kind of weakens our argument a little bit. Right? If you can prove something without assuming anything, then you should prove it without assuming anything. But because we're making this assumption, that means it's pretty essential to our proof. So we are going to use this somewhere, and in this case, we're using it right here. So all of this stuff can be replaced by k times k plus 1 over 2. But then we still have the plus k plus 1. And we need to show that this equals that right side. Well, if I look at my left side right now, and the right side. The thing that's very obviously different is the division by 2. On the right side, it's the whole thing divided by 2. On the left side, I just have one term divided by 2. So let's make the left side be completely divided by 2. So to do that, I can make a common denominator. And then we can simplify this a little bit. So I get k squared plus k plus 2k plus 1 divided by 2. So that's k squared plus 3k plus 1 over 2. And if I factor this, well, look at that. I get k plus 1 plus k plus 2 over 2. So I get it to look like that. So I've shown that supposing this works for some number, it'll definitely work for the number right after it. So that's the thing about the dominoes, right? Supposing one domino falls, the domino right after it falls. Now that itself isn't enough. That's where people get stuck up on, like, this feels like circular logic. But that's not enough to prove this, because we've just said that supposing one falls, the one after it falls, but we don't know that one fell. So here's where we need to do the base case to show that the first one falls down. Because then from that, then we'll know the second one also falls down, and then we know the third one also falls down, and so on. So now we're going to do a base case to show that for n equals 1, this works out. So for the first one positive integer, it's just 1. I want to check that that equals 1 times 1 plus 1 over 2. Well, that's 1 times 2 over 2 is 1. So yep, it works for our base case. So finally, we can write a conclusion that says that, therefore, by induction, we show that the sum, and in my conclusion, I try to repeat the language of the question, the sum of the first n positive integers is n times n plus 1 over 2. This is a little backwards on the proof. Usually you do your base case first and then you do your inductive hypothesis and inductive step. You can write it that way. Sometimes, like, the reason we do that, the base case first, is just to test, like, if the base case doesn't work, then you don't even have to do all the work for the inductive step. The reason I'm doing it this way is usually just the logic seems to make more sense when you do it backwards. Except it might give you extra work, because if you do all this work in steps 1 and 2 and then the base case doesn't work, the base case is one of the easiest things to check. So that's usually why people do that first. You can write it either way, but this is just, I'm showing you this process for it. So I would spend some time just reading through this proof again, trying to really think about that domino logic on this, and see if you can place all of these steps, see if you can, like, rewrite this yourself and think about it for yourself before moving on. And then there's one more, very similar to this one, where now you're proving that the sum of the first n positive odd integers is n squared. So remember, now we don't care about 2, we don't care about 4. We're looking at only positive odd numbers. So we're starting at 1, then going to 3, 5, 7, and so on. So try doing this one on your own. See if you can figure out how you can write it. Pause it, try it on your own, and then I'll show you how to do this one. Okay, so on this one, we start off again by writing out what we want to prove. So here we want to say that 1 plus 3 plus 5 plus 7 and so on all the way to n. Well, is it all the way to n? Let's check. So how do I write that last bit? I have the first n positive odd in numbers. This is the second odd number, right? This is n equals 2, but I have 3. This is n equals 3. This is for n equals 4. So my n value doesn't equal the same number that's in that spot. So I need to think about how to write an equation that will make it look like that. Something that's pretty standard that people try to draw from, and you can kind of see from this pattern, is to represent odd numbers. Usually you do 2n minus 1 or 2n plus 1. In this case, 2n minus 1 works because I can do 2 times 2 minus 1. That will give me 3. 2 times 3 minus 1 gives me 5. 2 times 4 minus 1 gives me 7. So instead of n here, I would need to write plus 2n minus 1. Sometimes your odd numbers are 2n plus 1, depending on how your index works. So that's a little hard to see on this one, but it's kind of how this one gets set up. Okay. So we're trying to prove that this, and this is why I like writing this out first, because if you write this out first, that gives you a sense of like what the numbers are, what the variable should be, what everything looks like before you actually start doing any math with it. And then you say it needs to equal n squared. So we'll do this one the standard way, where we do the base case first. So we want to show that the first domino falls down. Right? So for n equals 1. Well, for 1, that's my first positive odd integer. That definitely equals 1 squared. So my base case works. The first domino fell down. Now we need to show that as long as one domino falls, the domino after it falls. So that would be our inductive hypothesis. So we're going to say suppose 1 plus 3 plus 5 all the way to 2k minus 1, to some odd number, should equal k squared. Then our inductive step will be to show that 1 plus 3 plus 5 plus 2k minus 1 plus the next odd number. Well, to get to the next odd number, I can't just add 1 this time because that will give me an even number. I need to add 2. So this will really be, the next odd number will be 2k plus 1. Should equal k plus 1 squared. So now I need to do some math to show this. Well, again, kind of like what we did last time, we're going to have to use that inductive hypothesis somewhere. And I can see that this bit is the same as this bit, which I said equals k squared. So I can say that all of this equals k squared plus 2k plus 1. Well, that factors to k plus 1 squared. So I've shown my inductive step. So finally I can conclude, therefore by induction, we showed that the sum of the first n positive odd numbers is n squared. So again, go through this proof. This proof was pretty straightforward in the inductive step, but that 2n minus 1 bit was the more challenging part of this proof to write. Proofs are really where a lot of creativity comes out in math, a lot of different types of thinking. You really got to like play around with these numbers a lot to get these proofs to work. It takes some time to develop. More practice helps you on this, like most things in math. Okay, I can tell you, like when I first learned induction, it took me a really long time to first be comfortable with the idea that this is proving something, and also just like being able to do it and like find the things, the mathematical manipulations I have to do to these equations to solve it. The manipulations you're doing in this inductive step, that's really, really strong mathematical thinking to look at these patterns, to look at the substitutions. That's going to really, really help you in your math classes next year and in the future. So that's why like this is like one of those like introductory things that just has so many rich different things that you can go with it to really develop your mathematical thinking. We're going to stop with these two proofs for this week. I want you to get really comfortable just with these types of induction proofs. the induction process doesn't change, but there are a few other types of things that you can do, types of manipulation. So like in this one, the manipulation we did was using this inductive hypothesis to substitute in, right? That's what happened in both of these. So let's stick with this type of substitution manipulation thing and practice that this week. And then next week, I'll show you a few other manipulations that you can do to the math stuff to prove, to do your inductive steps. So I'll give you some practice proofs to do with this type of manipulation so you can really practice this. And then we'll move on to some more induction next week.